Hello, geometry students. Today we are going to review very briefly the algebraic properties of equality that we can use to justify statements in algebraic proofs. So we're going to be starting with equations, maybe a little geometry setup, and then using these algebraic properties to justify. So this is going to be our first glimpse at proof writing using some content that we're already familiar with from Algebra 1. So that's what we're going to be working on today. So we're going to dive right in. So properties of equality from algebra, these are the rules that we use to solve equations that maintain the equal sign, that maintain balance in equations. So for example, we have the addition property. So the addition property says that if you have an equal sign, that you can add the same thing to both sides of the equal sign and maintain that equality. So if A equals B, then when we add C to both sides, the equality remains. We can do the same thing with subtraction, multiplication, and division. Now division is unique because it has this added quality that what we are dividing by is not 0. We understand that division by 0 breaks math, right? It doesn't work. We're not allowed to do that. And the roots of all of that are based in calculus, and you can explore that later. But for the simple statement here, we can't divide by 0. And so as long as we're not dividing by 0, we can divide by whatever else we want. And that all maintains equality. So subtracting from both sides, multiplying by on both sides, or dividing by both sides, so long as it's not by 0. So those are your the first 4 there. And then we get into some that perhaps didn't seem as necessary when you were in algebra class, but we will use much more extensively in geometry. The reflexive property says that something equals itself. Think about looking in a mirror, right? You are yourself. The symmetric property allows us to switch the sides of an equal sign. So this is useful if you are asked to prove that x is 5, but when you work out the algebra, you get 5 equals x. Your final step will be to switch the two sides by the symmetric property. It's symmetrical. The transitive property is one of my favorites personally. It says if A equals B and B is C, then A equals C. So we have this cutting out of the middle piece, right, which is a concept that we saw with if-then statements previously. So we can take out that middle piece and just go straight to A equals C. That is a specific example of substitution, which we'll talk about momentarily. And lastly, we have the distributive property. This is another common one from algebra class, where if we have a quantity inside a set of parentheses, addition or subtraction, and we have a multiplication happening, that we can distribute that multiplication to each term inside the parentheses. Again, whether it's addition or subtraction. And then I had mentioned that the transitive property was just a subcategory of substitution. So if substitution says that if two things are equal, then you can replace A with B in any expression or equation. This would also justify steps like combining like terms, or simplifying 3 plus 5 to be 8, or simplifying fractions. Things like that are called substitution. So let's look at a proof together. I'm going to show you my style of proof. It's slightly different than how your textbook does it. So when we are given an equation, we're going to go ahead and set it up in that 2-column proof format that we discussed previously. So I have my statements on one side and my reasons on the other. And I like to number my statements and reasons just so that it's clearer for my audience. For whoever is reading my proof, it's a little easier for them to follow, especially if my statement takes up more room, or if I have to write a sentence occasionally for a reason. Sometimes they get offline from each other, and so this just helps the reader follow along. So always when you are writing a proof, you want to start with what you're given. So in this case, it's an equation, but it might be statements about a picture that go in that first spot, and then you just simply state that they're given. They are given that those things are true, and therefore that's my justification. So if I'm going to solve this equation, the first thing that I would do is I'd want to get rid of parentheses, so I would distribute. And so when I distribute, I end up with 2 times 5 is 10, 2 times negative 3a is negative 6a, and then distribute the -4, I get -4a, -28. And that was by the distributive property. So the style that I'm using is I am performing the action kind of in between here. I'm not showing it written out, and then I'm just immediately simplifying and calling it the distributive property. Your book would probably have that as being 2 steps, showing that they're distributing and then simplifying with the substitution. And I cut out that middle step. So from there, I'm ready to combine like terms. So this is where the substitution property allows me to combine the -6a and the -4a, and the 10 and the -28. And now I'm going to work on both sides of the equal sign. So I'm going to be looking at using addition property of equality to move that -18 over to the other side. And lastly, I would divide both sides by -10 to get that a is -11. And so this is my style. There are more examples in your text, but this is the method that I use when I am writing 2-column proofs with algebraic statements. So there you have it, using our properties of equality to justify steps in an equation, and our first glimpse at a 2-column proof.